Hello and welcome to the first lesson in the electric fields topic. In this topic we're going to be looking at obviously electric fields, how they work and the equations that govern them. In today's lesson we're going to be considering how the force in between two charges or two charged particles works. Firstly though, just a little bit of revision from GCSE. If we take two particles that both have a positive charge, from GCSE we know that those two charges will repel. If we have two negative charges, say electrons, they will also repel. If we have opposite charges though, positive and a negative, then we know from GCSE that those will attract. What we need to look at today is to get some kind of equation that's going to mathematically give us firstly how big that force of repulsion or that force of attraction is, and obviously also we need to make sure it gives us the correct sign to tell us which way that force is going to be acting. The law that governs the force between two charged particles is known as Coulombs Law. This is the same Coulomb after whom the unit of charge is named. Now Coulomb himself was a French physicist. He served in the French military and his life was at the end of the 18th century. So he was born in 1736 and died just at the start of the 19th century. What Coulomb's law looks at then is the force in between our two charged particles. Now for the purposes of this I'm not going to give them a sign just yet, but I'm just going to call them Q1 charge 1 and Q2 charge 2. Before we jump into the law itself we need to consider what factors are going to affect the force that's acting in between these two charges. The first thing I hope should be obvious, and it depends on the magnitude of the charges themselves. The second factor is the distance between the two charges. As we get further apart, the force between the two charges will get smaller and smaller. From the charges then, we require the product of the two charges, Q1 times Q2, and our force will be proportional to that. Now for distance, we know that the distance increases, the force decreases, but it's not quite as simple as saying F is proportional to 1 over R or F is inversely proportional to R. It's actually proportional to 1 over the distance squared. Now this particular law is known as an inverse square law. And we'll look a little bit more at inverse square laws in just a moment's time. To tie all of that together then, we can say that force is proportional to the product of the charges divided by the square of the distance between them. Our next step is to take the proportional sign and to replace it with the equal sign and some constant. In Coulomb's law, the constant itself is actually made up of a couple of different parts and is this. It's 1 over 4 pi multiplied by epsilon naught. The reason why it's 1 over 4 pi epsilon naught is because that constant itself, epsilon naught, is used elsewhere in electric fields, in electrostatics, electrodynamics and electromagnetism. That's why we don't absorb it and just make it one constant. The name for epsilon naught is the permittivity of free space. And the value for it is 8.85 times 10 to the minus 12. The unit is farads per metre. Now farads we haven't come across yet. We'll look at that more when we do the capacitance topic. Permittivity is just a term to tell us how electric fields propagate through free space, or obviously another word for free space is a vacuum. In order to tie this all together then and give the full version of Coulombs law, we can now write F is equal to Q1 Q2 over 4 pi epsilon naught r squared. And that now is our full version of Coulombs law. We now need to look at the couple of features in Coulombs law that give us information that we might not realise at first we're going to get out of it. Firstly, let's just put back on the screen the full version of Coulombs law, Q1 Q2 over 4 pi epsilon naught r squared. Now when we first looked at Coulombs law, we purposely said that we weren't going to put a sign on any of our charges. But now let's have a look at what happens when we do consider the signs of these charges. So we're just going to draw ourselves a quick table. Okay. Let's see what happens when we make both Q1 and Q2 positive. Well, we can see from the equation on the top line that we're taking two positive numbers and multiplying them together. That will therefore give us F as positive. If we take Q1 and Q2 as both negative, on the top line of our equation, if Q1 and Q2 are both negative and we multiply them together, we get F once again being positive. Where we have Q1 and Q2 having the opposite signs, one positive and one negative, going back again to the top line of our equation, if we multiply a positive number and a negative number together, we know that we're going to get our force coming out as negative. Going back to the first slide, we know that when we have two like charges, they are going to repel, and when we have two opposite charges, they are going to attract. Therefore, we can see that the sign of F, whether that be positive or negative, doesn't just tell us the direction that we're used to with vectors, but actually tells us whether the two charges are going to repel or are going to attract. If we get F as positive, we know that we've got a repulsive force. If we get F as negative, then we know we've got an attractive force. Secondly, let's have a look at this term inverse square law and what it means. Now, if we were to draw a graph of the force against the distance between our two charges, the graph is going to look something like that. Just to rewrite the proportionality relationship back on the screen, F is proportional to 1 over r squared. If we take a point here, R, and we have a look at what the force is at that point, if we were to double R and do exactly the same thing, what we should find is that the force has now become a quarter of the original force. if we think about our proportionality, we're now saying 1 over 2r squared, which will give us 1 over 4r squared. Our force has therefore gone from its original value down to a quarter of that value. Taking it further, if we were to take the distance from r and make it 3r, our inverse square law tells us that f will become 1 over 9 times the original value. In other words, 1 over 3 squared. Now, that idea of an inverse square law is an extremely important one in physics, and you're going to come across a few inverse square laws this year in the different topics, and you'll find that if you do take physics study further up to university, you'll find that inverse square laws actually come out quite a lot in our theories. So now let's try an example. Calculate the force between a plus 4 nanocoulomb charge and a minus 7 nanocoulomb charge placed 2 millimeters apart in a vacuum. As usual, pause the video, have a go yourself and come back once you've got an answer. If we rewrite our equation, firstly, F is equal to Q1 Q2 over 4 pi epsilon naught r squared, we can pretty much go straight in and start plugging numbers in. Our first charge is plus 4 times 10 to the minus 9, and we multiply that by our second charge, minus 7 times 10 to the minus 9. That is going to be divided by 4 pi times epsilon naught, which is 8.85 times 10 to the minus 12. And then we're going to multiply that by our distance. Well, 2 millimeters is 2 times 10 to the minus 3 meters. And then we're going to square that. It's highly important that you remember to square that r. Most of the mistakes that I see people making with this kind of question are forgetting to square that distance, or maybe thinking that 2 times 10 to the minus 3 squared is 4 times 10 to the minus 3. It's not. It's actually 4 times 10 to the minus 6. The best way to do it is just to make sure that you get all of this correct in your calculator. As long as you have plugged it into your calculator correctly, what your calculator should tell you is that we get a force of minus 0.063 newtons, or we can write that as minus 63 millinewtons. The minus sign, of course, here denotes that we're going to get an attractive force between the two charges, which is exactly what we expect, considering we've got a positive and a negative, we have opposite charges, and therefore we expect them to be attracted to each other. So to summarise then, in this video we've mainly looked at Coulombs Law, and Coulombs Law says that F is equal to Q1 Q2, so that's the product of the charges, divided by our constants, which are 4 pi epsilon naught, and we've also got divided by r squared as well. Now we also looked at how the sign of the force works, so remember, if F is positive, then we will have those two charges repel, we'll have a repulsive force, and of course if F is negative, then those two charges will attract. We've also looked at some of the facets of an inverse square law, so remember that F is proportional to 1 over r squared. Now of course what that means is that if we go from r to 2r, so we double the distance, then the force will end up being 1 over the square of 2 of that, so it'll be a quarter of the original. If r goes to 3r, then F goes to F over 9, and so on and so forth. So that's it for this video. As usual, thanks for watching and I hope you found that useful. There is an extension question to this video which is in the electric fields playlist. If you're a top level student, if you're aiming for A or A star, then I suggest you at least have a look at that extension question and just try to push you a little bit. Other than that, I'll see you in the next video.